Okay, we're going to talk about Unit 4, Day 4 today. So complex numbers. These are numbers that before, whenever we'd say like a square root, a negative, we say can't do it. So we just kind of move on. But now we are going to define it at least so that we can work with those numbers. Because there are some situations, I believe in when you're measuring currency, if you're an electrician, these numbers do, I want to say exist. They kind of don't exist, but they kind of do exist. So we do want to talk about them. They're called complex numbers. So learning target number 1, I can identify a complex number. I can also add, subtract, and multiply complex numbers. And I can find the complex conjugate of a given complex number. So a lot of that probably sounds like a whole bunch of mumbo jumbo, a whole bunch of new vocabulary there, but let's get started here. So what is the square root of negative 9? Well, for right now, we just say it doesn't exist. So it doesn't exist. It's not defined. We can say undefined also. But what is the square root of negative 9 squared? Well, what does a square and a square root do to each other? If you remember, they undo each other. If I said the square root of 9, that'd be 3, and I said now square it, 3 squared is 9. So the squared and square root wipe each other out, so this would be negative 9. Even though the square root of negative 9 doesn't exist, I can square it and get negative 9. So we really need the square root of negative 9 to exist. That way we can do some of these operations. So the fix to this, the fix is what's called imaginary numbers. Imaginary, meaning they don't exist, but like I said, we're going to pretend like they exist because we need them to. We need these to exist so we can do some operations with them. So in order to complete the computations, we let the square root of negative 1 equal I being imaginary, the imaginary numbers. So here, these complex numbers are actually anything you can think of. So before today, this is what you knew. Okay, you knew real numbers. You knew your irrational, rational, like you've dealt with all of these in your math career. So whether or not you could identify them or get all these right, that doesn't quite matter, but you've seen all these before. Well, now we're going to add a little chunk over here called imaginary numbers, and they are all under the realm of complex. So, we used to think real numbers is anything you can think of. Well, real numbers are anything that exists. Now we got imaginary numbers, and put them together, you got the complex numbers, which is everything. Okay, so some examples here. One of the properties of radicals is you can split what's under the radical into factors. So like if I have the square root of negative 36, I could actually do factors of negative 36, which would be negative 1 and 36, put them under radicals, and this is going to equal the same thing. So if you split them into factors and they're still under the radical like this, now what's the square root of 36? Well, the square root of 36 is going to be 6, and then the square root of negative 1 we're just going to call I. So this would be 6i. If we were solving for x, I'd need to put plus minus, if we were solving, but we're just going to put the principal root, the positive root of 36, and say it's 6i. So if I said x equals this, then it would be positive and negative, so positive 6i and negative 6i. Okay. Radical negative 50. Again, I could do the factoring. Okay, so in fact, it might be easier to do it this way. So factoring would be 2 and 25, and this would be 5 and 5. And so this I could write as, I'll put the radical negative 1 on the end this time. I'll put it on the right side. And this would be radical 2. I'm going to stop right here and put radical 25, like that. Now, when we do a factor check like this, a lot of times we say, if you see a pair of something, pull it out. So I see a pair of 5s, that's right here. The square root of 25 is 5. So technically I pulled a 5 out from under the radical. And then in the radical 2 I can do nothing with. And then the square root of negative 1, we've got my I there. Okay. Now the order of these, and I don't know how they decided this, I don't know why they decided this, but they want real numbers, or the whole numbers here, the integers first. And then they want imaginary, and then the irrational, so the radical 2, like that. I have no idea. They always want the radical last. So imaginary should go between them, and then imaginary, or the irrational, the radical goes last. Here I've got 7. Don't forget about that. You got your 7 here. I've got a negative under here, so I'm just going to automatically put I, because there's going to be an I in my answer. Now, I might be multiplying 7 by more things, so I left a space. Now that 108, remember, let's look for pairs of factors. So if there's a pair of factors, I can pull 1 out from under the radical. So 108, a lot of different ways you can do it. I did 4 and 27. And then 4 would be 2 times 2. There's a pair. And then 27 is 3 times 9. 3, 3. So there's a pair. So I have a pair of 2s, pull a 2 out. Pair of 3s, pull a 3 out. And then what's left, I still got a 3 I never used. So that's still under the radical. So radical 3. So I got 7 times 2 times 3. Well, 7 times, and that'd be 6. So it'd be 42i radical 3. And that's your answer. Okay, go back and circle these. Negative 121. Now, 121 is a perfect square, so we can save some time. What's the square root of 121? 11. And then since there was a negative under there, it's I. Because this would have been the square root of 121 times the square root of negative 1. Simplify those, you get 11, and you get I. So now, complex numbers, by definition, have 2 parts. So a complex number is written in the form a plus bi, where b does not equal 0. If b equals 0, it's just a real number. Still considered a complex number, but a real number is a more specific term for it. So it would just be a real number with 0 as the imaginary part. So it's just kind of a waste to put it there. So let's go down here now. When I'm adding or subtracting, so again, adding or subtracting, you kind of do the same thing for both. So they get lumped together. So think you want to do common terms or like terms. So if you're adding complex numbers, you want to add or subtract the real components and then add or subtract the imaginary components. So think like these look like terms. So 3 plus 5 is 8, and then 9 minus 2, 9 plus negative 2 would be 7i. And that is all you do when you're adding complex numbers. It really is that simple. 4 plus negative 4, 0. Negative 3 plus 3i, that wipes out 2, so technically it's nothing. That'd be 0. Okay, so these are opposites of each other. When you add them together, you get 0. The subtractions where some people make mistakes. Remember, you're subtracting both of these terms. You're subtracting negative 2 and you're subtracting positive 4i. So you can just do it that way. You can think of minus these, or you can add the opposites. It might be easier just to add the opposites, because we don't typically mess up when we're adding. So 5 plus 2 would be 7. Negative 3i plus negative 4i would be negative 7i. Now this was meant to be at the top of the next page. For some reason when I printed it, printed on the bottom of this, but it's meant to be on the back of the next page to help us out. So I might copy this over to the top of the next page if you might want to do the same thing. So this was I'll pause this. So it's supposed to look something like this. So I by itself is this radical negative 1. But what if I squared that? What if I squared the square root of negative 1? So on this one, I'd have negative 1 square root squared. Well, that's going to be just negative 1. So every I squared you see, you can think of it as negative 1. I cubed would be the same thing as I squared times I. We just learned that I squared is negative 1, so this would be negative 1 times I, so negative I. This is when we're simplifying stuff, it's kind of easy to know this stuff. Now, I to the 4th is going to be a little tricky. I to the 4th is the same thing as I squared times I squared. What's I squared? I squared is negative 1, so this would be the same thing as negative 1 times negative 1. Well, negative 1 times negative 1 is 1. So I to the 4th actually doesn't change anything. If I said I have 3i to the 4th, it's the same thing as 3, because I to the 4th is just 1. I to the 5th, I could think of this as I to the 4th times I. Well, I to the 4th is 1, so this would just be I. So I to the 5th actually simplifies I. It's like every 4 that you see, you just throw them out. For every 2 that you see, you switch the sign. Okay. So here, I to the 6th, Well, there's 4 in there. I could throw that out. So I to the 4th is going to throw that out, but you still got I squared left over. A little messy here. I to the 4th is 1. I squared is -1. So I to the 6th is the same thing as I squared. I to the 5th is the same thing as, what did we mess up here? As I to the 1st, which is just I. So for every 4 you move up, they repeat themselves. Okay, and every 2, -1, +1, -1, +1. It's going to be alternating. Okay, so user distributed property, more necessary here. So if I get 2i times 3i, that'd be 6i squared. And we said I squared is a -1, so I just write -6. Here I've got 5i times 8, so it's 40i minus 15i squared. Well, I can't simplify, but I squared can. I squared is a -1, so if I took this out, that's going to switch that sign. And we like to have the real component first, followed by the imaginary component. So this is the correct order, 15 plus 40i. If I'm multiplying binomials, make sure you FOIL. So 2 times 1 is 2, minus 6i plus 5i minus 15i squared. Again, anytime you see an I squared, throw it out, change the sign, because I squared is -1. So I got 15 plus 2 is 17 minus I, because you get -6i plus 5i. 6i times 9i, that's 54i squared, plus 30i minus 9i minus 5. And I squared is worth a -1. So if we got -54 minus 5, that's -59. And then plus, I got 30 minus 9, so 21i. If I don't move enough, my lights go out in my room. If I'm doing this, just write it twice. If it's got it squared, 9 times 9 is 81. 9 times 4 is 36i. Notice we're going to do the exact same thing again. The outer product and the inner product are the same. And then 4i times 4i would be a 16i squared. Remember, I squared is a negative, so it's going to switch that to a minus. So I got 81 minus 16, that's 65. And then 36i plus 36i would be 72i. So like terms. Let's see, this last part here is actually easier than it seems. It makes our life way easier. Whoever discovered this, I am very thankful they discovered this. These complex conjugates are complex numbers whose product is a real number. And notice, what's the difference between these two? The only difference is the sign. So if I gave you 1 and I said, what's the conjugate? Switch the sign between them, make it a minus. Or if I said, what's the conjugate of this guy? Switch the sign to plus, and there's the conjugate. So these guys are conjugates of each other. So if I FOIL this, I want to do it the long way one time, that'll hopefully present a shortcut. A times A is A squared. This would be a negative ABI, and this would be a positive ABI. So what happened to those middle terms? They cancel each other out. The i's are gone. And then positive BI times negative BI would be a minus B squared I squared. But what's an I squared? I squared is always a -1, so it's going to make that a plus. So this would just be here, A squared plus B squared. I don't know why I wrote this twice here. So notice the i's disappeared. This is a real number. A was a real number, B was a real number, A squared plus B squared is a real number. So I'm multiplying these numbers that don't exist, and the result does exist. Okay, so let's try this here. So I've got 5 times 5 is 25. If you want to take a shortcut, the outer plus the inner are going to wipe each other out, because this would be a -20, that'd be a +20. So I don't have to write the outer and inner products. The last terms then would be a -16i squared. Cross that out. 25 plus 16 is 41. We got a real number for an answer. So notice it was just the first number, 5 squared, plus the second number, 4 squared. Even though positive times negative is negative, this I will always make that back to a positive. So it's always going to be a plus too. So pretty easy. If I want to use that shortcut, look at this number, look at this number. -2 squared is 4, -3 squared is 9, add them together, 13. If you don't believe me, go and FOIL it out the long way and you'll still get 13. Okay, identifying here. So find the complex conjugate. So what's a conjugate of this guy? Well, the first and the last term don't change. It's just the sign between them. So that'd be a minus. Conjugate of this guy, be careful. Don't switch the -4. It's the first number, the second number, and switch the sign between them. Make it a plus. Okay. Shortcut, first number squared plus the second number squared. 4 plus 49 equals 53. You can do it the long way if you want, but it's a lot faster. First number squared, so -4 squared plus the second number squared. They were negative, but when I square them, they both become positive. And I get 65. Okay, so don't overthink those. Don't overthink conjugates. They're easier than they look.